All right, let's talk about one of the most incredible yet totally invisible journeys happening all around us, all the time. The path electricity takes from a massive power plant across hundreds of miles of wire straight to the plug in your wall.
You know that feeling, right? You walk into a dark room, you flip a switch, and boom, the lights are on. It feels instant, but what's really going on behind that simple action? Well, we're going to pull back the curtain on that whole hidden process from the moment electricity is born to the second it powers your life.
So, where do we even begin this journey? We have to go all the way back to the start, to the fundamental physics, the very spark of the idea of how we create the alternating current, or AC, that runs pretty much everything.
Okay, so pretty much this whole thing, our entire electrical grid, it all comes down to one core principle discovered by Michael Faraday. He figured out that the secret ingredient isn't just magnets and wires, it's change. If you just stick a magnet next to a wire, nothing happens. But the moment you start moving it, see what's happening here? It's this natural push and pull. The magnet goes in, current flows one way. You stop, it stops. You pull it out, the current flips and goes the other way. And that right there is where the name alternating current comes from. It's literally alternating its direction. Okay, so now imagine that instead of someone moving a magnet by hand, you have a giant, massive turbine spinning at a power plant. That simple back and forth motion suddenly becomes this beautiful, smooth, continuous wave of electricity. And that's the signature look of AC power, the sine wave. Now, this wave has a couple of key things we need to know. There's the amplitude, that's basically its height or voltage, and then there's the frequency, which is just how fast it's cycling up and down. Here in the US, the standard is 60 times a second, or 60 hertz. And that's not just some random number. It actually had a big impact on other tech. Think about old TVs. They ran at 30 frames per second because it was super easy to sync up with the power grid. You'd get one new image for every 2 cycles of electricity. But here's a cool thing. Power plants aren't just sending out a single wave. To be super efficient, they actually generate 3 identical waves, but they're slightly offset from each other. This is called three-phase power, and it gives you a much smoother, more constant delivery of energy. It's absolutely essential for running big, heavy-duty machinery. All right, so we figured out how to make AC power. But why AC? Why not DC? You know, the stuff that comes out of a battery? The answer is AC's superpower. It can travel crazy long distances without losing much energy. And the secret weapon that makes this all possible? The transformer. Remember Faraday's law? We need a changing magnetic field. Well, because AC is always changing, it's perfect for transformers. It creates that changing field automatically. Steady, flat DC power from a battery? It just can't do that. So, to get power across huge distances, power companies use these transformers to jack the voltage way, way up. I'm talking like 200,000 volts or even higher. It sounds terrifying, right? So why on earth would they do that? Well, this chart shows you exactly why. When you crank up the voltage, the current drops way down. And less current means you lose way less energy as heat in the power lines. I mean, just look at that difference. Trying to send power at low voltage is like trying to carry water in a bucket full of holes. You lose most of it before you even get there. So, after that super high voltage electricity travels all the way to your neighborhood, another transformer does the exact opposite job. It steps down the voltage to a much safer, much more usable 240 and 120 volts. That's the power that actually goes into your house, ready for your appliances. Okay, the power has made it. It's right there in your outlet. But what do we do with it? We think about lights, our phones, computers. But the single biggest user of electricity on the entire planet is this kind of unsung hero, the electric motor. And this is where the system is just so elegant. There's this beautiful symmetry to it. We use a spinning thing, a generator, to create electricity. Then we send that electricity hundreds of miles away to power, well, another spinning thing, a motor. It's a perfect loop. But you know, not all motors are the same. It turns out that something like 90% of all motors in the world are a specific type called an induction motor, which Nikola Tesla patented way back in 1887. This thing is the workhorse of our entire civilization. It's in everything from giant factories to the air conditioner in your window. The absolute genius of Tesla's motor is how ridiculously simple and elegant it is. Get this. There's no direct electrical connection to the part that spins, the rotor, none at all. Instead, the stationary part creates a rotating magnetic field, and that field induces a current in the rotor. basically making it chase the field around and around. Fewer parts, nothing to wear out. It's just incredibly reliable. Okay, but there's a catch. That amazing rotating magnetic field, it needs that three-phase power we talked about. But your house only gets single-phase power, so how in the world do you get a motor started with just one phase? Turns out, you need a little bit of a trick. And that trick comes from a little device called a capacitor. Now, to get what it does, think about pumping up a tire. When you start, the airflow is at its max, right? But the pressure inside the tire is at its lowest. By the end, the pressure is maxed out, but the airflow has slowed to a trickle. They're out of sync. A capacitor does the exact same thing with electricity. It creates a delay, so the voltage peaks just a little bit after the current does. And that little time delay, that's the whole ball game. You feed the main power to one set of coils in the motor, and you feed this delayed power from the capacitor to a second set of coils. And just like that, you've created a fake rotating magnetic field. It's not a true one, but it's enough of a nudge to get the motor spinning.
So let's recap. We've made the power, we've sent it across the country, and we've used it to spin a motor. But there's one last really important piece to this puzzle: control. How do we go from just on and off to making these motors do exactly what we want as efficiently as possible?
Well, the answer is something called a variable frequency drive, or a VFD. Think of it like a brain for the motor. First, it takes that nice smooth AC power from the wall and rectifies it, turning it into flat, stable DC power. Then, its little computer brain starts chopping up that DC power into thousands of tiny pulses to perfectly fake a brand new AC wave at whatever frequency it wants. This clever technique is called pulse width modulation, or PWM. By changing how wide those little DC pulses are, the VFD gets total, precise control over the motor's speed. So instead of just being on or off, it can run at 30%, 50%, 72%, whatever it needs. This saves a ton of energy. And that leads us right to the cutting edge, which is actually already here. It's called the electronically commutated motor, or EC motor. What this does is take that whole VFD brain and build it right into the motor itself. The controller and the motor become one perfectly tuned package. The result? Unbelievable efficiency and control. And just like that, we've gone full circle. We started with Faraday just moving a magnet inside a coil of wire, and we've ended up with a smart, integrated motor with its own brain. It really makes you wonder, what's the next spin in this amazing story of electricity?